share your screen too. Okay.
The right one. Is it the one or not? No, wait a second. I think there's a couple of screens here going on, so it should be this one. Desktop.
Okay.
Okay.
Yeah, I can see the screen. Okay, so hi everyone. Let's get started. So today we have less people, the fewer people. I guess that is a mix of the early, I mean, like it's February, like and then also like we have the webinar on Tuesday, like not our usual Wednesday. So, but anyway, hopefully like we have a good time here. So hi everyone. Thank you for joining the February BNP webinar. It's a great pleasure to have Xenia Miscouridou from the University of Cyprus. And like as usual, we'll have a 45 and 50 minutes presentation followed by a 10 to 15 minutes Q&A session. Please welcome Xenia.
Thanks, Joachim, so much, and it's great to kind of see you all. Thanks for this invite. And yes, I guess I could get started. So I'll present some work of me, Juho, and Francois. Relatively recent one when we all were back in Oxford, where although now me and Juho left, Francois is still there. And this is a work on approaches towards practical Bayesian nonparametrics, if I want to put under that umbrella term. And more specifically, it's about we can practically approximate completely random measures. And by practically, I mean how we can have nice finite approximations of those in IID distributions. So I want to start with some introduction, explaining the motivation behind this. Then I'll talk about the formulation. How do we actually formulate this framework, which we call a unified framework that can give rise to the approximations? We show several examples on specific measures that are very popular in literature and that we're interested in. Then I'll talk about how we quantify the error introduced by the approximation. And maybe the most important thing, how we can actually use this practically in posterior inference, why this makes sense, what results we get, and how you can also use it in your applications. So, it's a Bayesian nonparametric seminar, so hopefully I don't really have to, motivate Bayesian nonparametrics, but we all love them because they give us probabilistic models that are flexible and they're data adaptive. And we've seen a lot of applications in literature around clustering, spatial statistic density estimation, recommended systems, and network modeling. So in a lot of these cases, and a lot of these interesting cases rely on infinite activity completely random measures. So there is this infinite component coming in. Personally, I'm interested in how we can use these infinite activity completely random measures to model graphs. For example, following work of Francois for the Caron-Fox model specifically, we can use this infinite activity completely random measures to model the whole range of dense to sparse graphs. But of course, we still have to deal with that infinite component. And not just in this network modeling, but in all of these applications, we have to face this number of practical challenges in posterior inference and sampling. So whether you do MCMC or some sort of variational inference, an approximation has to come into the picture. So whether it's Gibbs or it's a sequential Monte Carlo or slice sampling, again, some sort of approximation comes, and most of the time is kind of case specific. So this completely random measure is essentially, an infinite series of weighted atoms. And since we have to somehow approximate it, there are two ways in general, like as a general approach. The first one is, since we have an infinite series of weighted atoms, we need to truncate this series and capture the best part of it, the best, I mean, the largest weights of these atoms. So ideally, we want to have this ordered and then kind of capture the first n. Or alternatively, you can just define another finite measure or, a density where you can sample in an IID way n atoms, and that measure approximates the true one. So ideally converges, in distribution to the original complete random measure. So what we're trying to do here is very nicely illustrated by the beta process, for example. And what we want to do and what we propose in this paper is to do this that I'll explain now, but for other completely random measures. So for the beta process, we know from literature, from this paper, that there is a series representation, is specifically the inverse Levy representation, where this infinite series of weighted atoms can be sampled by products of beta random variables, and that's how we obtain this sequence of stochastically ordered weights, and it's used in posterior inference. And similarly, in another piece of literature, gives us also an IID approximation for the beta process. In this paper by Kakramani, we know that if you sample these beta random variables, different parameterization here, we get another finite measure, which we use in practice to do the posterior inference in these models. So similarly to this beta process example, where we have here a series representation and at the bottom we have an IID approximation, what we propose is a way to have both of these for any completely random measure. And then for specific cases that we're interested in, we show the closed form distributions from which to sample from and get the representation in a series or in an IID way. But think about it like the beta process, but for other measures. So here, I'm not gonna go through all of this, but in literature, there's been, of course, a lot of approaches how to approximate these measures for the gamma process, for the beta, for the generalized gamma, stable beta. There's been there's a Perman, Pitman, and Yor, the size bias, the inverse Levy. So there's a lot of approaches, but they're not necessarily a lot of connections between them, links, or kind of a unified way that gives rise to both a series and an IID way. So what we propose is this framework to obtain both of them, so both series representations and IID approximations. And very briefly, the idea is to, once you want to approximate a complete random measure, essentially a Poisson random measure, we extend the space. So we construct everything on an extended Poisson random measure space. And what we obtain is, if I start with the examples, we get these novel series representations for the generalized gamma and the stable beta process, which interest us because they give very nice applications, such as, for example, the graphs that I'm interested in. We show connections between different parts, of the literature that propose approaches, and now we show how one, is a special case of the other and how they connect. Our approach is directly a generalization of the size bias construction of Perman, Pitman, and Yor. And a special case of our approach is this inverse Levy measure construction, and as well as a few others. And we also, quantify the error and derive and generalize posterior algorithms such as the slice sampler of Walker to do inference. So our setup, again, I tried to keep it light in maths here, but we write G as our completely random measure. So G is a realization of a completely random measure, takes this form of an infinite sum of weighted atoms. And here we parameterize it by rho and mu. So rho is this Levy measure that dictates the distribution of the weights, so these W's, whereas mu is this measure for the location of the atoms. So since this is an infinite random measure, completely random measures, this series is infinite. So essentially we have infinitely many small atoms, and these are the conditions that give me the infinite activity. The main ingredient that will come again and again in the next slide is this rho. So the measure for the weights, for which we're going to take the choices of a generalized gamma, a stable beta, or a gamma, and then we show how we can approximate that, how we can derive a distribution to approximate in an IID way, and so on and so forth. So, pointing out the two families of completely random measures that I am specifically interested in. The first one is the generalized gamma, and then a special case of this is the gamma, and also the stable beta, which has a special case, the beta, that I've shown before. So why these two? They give a number of interesting properties when it comes to models. They give interesting properties in the graphs, in sparsity, in microclustering. So these two are processes for which we do give novel series representations. And in the experiments, I'm using the first one to show how it behaves. So just stating out the objective of what I have, what I construct. Given this G, whether this is coming from the generalized gamma or stable beta, the target is to find a way to simulate and sample this G such that the weights are stochastically ordered. Then we show from which distribution to sample the weights so that we can have access to this Gn, the sequential truncated representation, which is essentially exactly this one. How can you sequentially sample these weights so that they're stochastically ordered? The second form that we're interested here, and we propose a distribution to capture this, is the exchangeable truncated representation. What I mean by that is that I might not care about having the first n atoms in this order sequentially, but all I want to say is that conditioning that this is the last atom, I just want to have access to a permutation of the previous ones, hence exchangeable. And lastly, if I don't want to have a series, so I don't have a sequential representation, whether it's in the series form or exchangeable, this part here is all about this finite measure from which you can sample in an IID way the weights in the atoms, and we show how this converges in distribution to the original infinite G. So there's three formulations here that we're interested in, and for each of these three, we give the form to construct the distribution to sample the weights. So the sequential truncated, atoms stochastically decreasing, the exchangeable, so we're conditioning on the last one, the previous are obtaining any sort of permutation, and then the finite IID is another measure which converges in distribution, and then we can just sample an IID wave from it. So the idea is this one. We construct an extended Poisson random measure. Once we have this complete random measure that we want to target, we introduce another dimension here, the dimension of time. So what we say is that imagine that these atoms, with weights, W's, and locations, theta, now are also equipped with some sort of time arrival. So they're in this race. And then we introduce an arrival time distribution in a way that the weight and the time are inversely proportional, and therefore the larger the weight, the shorter the time that they arrive. So we introduce an arrival time distribution such that the higher weights, the desirable ones, come earlier, as the figure suggests here. Then once we introduce this time, now we augment our Poisson random measure, and we're able to generate our times, our weights, and our locations sequentially. Ti being the arrival time, weight being the size of the atom, and theta the location. And here I have an illustration of this where for different arrivals, we sample the time and we sample the weight, and you see how the atoms are decreasing. If I choose a deterministic arrival time, the atoms are, this is the best sort of ordering because they're not just stochastically decreasing, they are almost surely decreasing. If I choose an exponential arrival time, there is some sort of stochastic decreasing. Again, it's not super clear, but that's the case. If I choose a gamma one, it's clear how these weights decrease. So the idea is you choose an arrival time distribution, we augment the Poisson random measure, and then finally, given all these properties and the theorems of the complete random measure, we can recover the original G. So we can, discard Ti, we can integrate them out, and then we recover our original N. So we're just back in where we wanted to be. Now, what does this mean practically? How does our theorem work? Given some sort of arrival here that you define, which is lambda, and given the Levy measure rho that you're interested in, like the generalized gamma, the stable beta, or anything, we construct these distributions phi and curly phi by exactly these ingredients, so rho, lambda, and psi. Now, psi are essentially the Laplace functionals. They are the interclass of the CDF of lambda and the density of lambda. So I'm just constructing these two distributions, phi and curly phi. And then I know that the sequential construction for my G with the stochastically decreasing weights is the following. The arrival time is exactly equal to this inverse of my capital Psi, evaluated at the unit rate of a Poisson process. These X's are the unit rate of a Poisson process. Then the weights given the times are coming from this distribution here. And then my locations just come from my mu as usually, and here time doesn't appear at all. So this first distribution and the inverse of this capital Psi are what mattered for me to construct a sequential construction. So it does matter whether I can actually invert this Psi, and the cost here is that I have to invert it for every I. So for every I, we set the arrival time, and then we sample the weight given the arrival time. Now, the exchangeable truncated construction works a little bit different, because now we don't have to invert this Psi, capital Psi every time, but only once. So this is saying you only need to sample the nth plus one time, and then conditional on that, you can sample all the weights, all the previous n weights from the second distribution that I have here. So this is better in the way that I only need this inversion once. So if it's hard for me to invert it, and if I need some sort of numerical way, I only have to do it once. So it's more efficient. Therefore, these two distributions now tune my sequential, my exchangeable truncated construction. And then the last one, which is the IID way, so this finite measure that converges in distribution to my original one, is just like a reparameterization of the exchangeable one. So by just evaluating this exchangeable distribution in some increasing function h, I get the finite measure, which I'll show more concretely in a couple of examples in a bit. And again, this specific one doesn't require any inversion. It only requires that this bit here admits a closed form. So the first example that I don't want to spend a lot of time is if I take my arrival times to be deterministic. So in the deterministic arrival time choice exactly corresponds to recovering the inverse Levy construction. Because what it says, if you want to sample from the sequential construction, you need to sample weights that are equal to the inverse of this tail of the Levy measure, evaluated of a unit rate Poisson process. And this is exactly the inverse Levy construction. Whereas the exchangeable and the finite IID construction correspond to exactly sampling weights that are above some threshold. So this is recovering the case in literature that corresponds to the epsilon truncation, with the only difference that we generalize here now epsilon, because it's not fixed, it's random. It's 1 over the time. I find much more interesting the exponential arrival time case, because now, if we focus on the generalized gamma process and we take that exponential arrival time case, we end up with a sequential and exchangeable representation having these nice closed forms. So the sequential construction is constructed by setting times in this way here, and then sampling the weights given times from the gamma distribution. Nice closed form. And then the exchangeable also has a nice closed form, which we found could be the so-called exponentially tilted BFRY originally in this paper. And the IID construction also has a closed form, which is this exponentially tilted BFRY proposed independently, like in this paper by Lee, James, and Choi. Now, this distribution has a generalization, which we find when we take another arrival time distribution, and specifically the gamma arrival time. So the gamma arrival times, which we can also view as a generalization of the exponential arrival times, give us some very cool properties. Why? If I focus on the generalized gamma process again, and I choose these arrival times to be gamma, my sequential distribution is again a closed form, is gamma, very nicely. The bad thing about this is that the times need to be inverted from my psi, and psi doesn't have a very nice form here. So the inversion is not necessarily nice. However, the finite IID construction, which admits a form that is a generalization of the exponentially tilted BFRY, has very nice properties. So firstly, this does have a nice closed form. It's just a bit long and ugly, and I didn't write it here. But the good thing about this distribution is that it's very easy to simulate, as we show in the paper. And it's a conjugate prior to a Poisson, to a gamma, to a Pareto, and to a normal with a fixed mean. So in all these models that we're interested in, that are usually kind of Poisson or gamma, at least kind of those I personally view, there's great conjugacy going on. And I want to stay a little bit in these gamma arrival times because they give us very nice representations. They essentially, all the constructions are useful, but the sequential is a bit impractical because you have to do that inversion, and that's not very easy. But the exchangeable is very useful. The finite IID is a nice new construction and is fully tractable, and it has the conjugacy. And I show an application of this case at the end. Now, another nice case is coming from the inverse gamma arrival times. So if I take this inverse gamma arrival times, there's two nice things going on. The first one, we get some other novel series for the GGP that specifically come from this generalized inverse Gaussian. So for the choice of a GGP and an inverse gamma arrival, we get an exchangeable representation that gives us a generalized inverse Gaussian distribution, and it's both tractable and new to our knowledge. And the other interesting fact is that for the beta process, if we use this arrival, the inverse gamma, we recover the IID construction that's known in literature by Griffin and Gahramani. However, now we also get the corresponding sequential one because these two come in the same package. The generalized Pareto, maybe I'm not gonna stay here for a bit, but it's another choice we tried. Let's try this arrival distribution. What does it say for the stable beta process? And again, we get some closed form distributions, which is really nice, and they're easy to sample from, although kind of huge here. And the nice thing is that these distributions that we get for both the sequential and the exchangeable construction, again, admit these conjugacy properties that the beta distribution has. So whatever the beta is conjugate to, this distribution again is conjugate to, and we can sample them exactly for the stable beta process. Now, that's how it works for the generalized gamma and the stable beta in their cases. How does the error behave? So what we do in the paper is, so we discussed the asymptotic error when using this truncated series representation, both in the normalized and the unnormalized completely random measure case. And also, so firstly, we talk about, what's the error between the CRM and its truncation, but then in the paper, we also talk about, what's the error in the actual hierarchical model when it's used there. So the error we look at is this L1 error. So literally, what is the sum of the weights that are left behind once we truncate at n? And in order to characterize how it behaves for large n, we place two assumptions. So the assumptions are really not strong. The first one is about this measure rho to have a regularly varying density, which is the case for a generalized gamma and a stable beta. And secondly is this assumption on the arrival time distribution, which again is something that is satisfied by the exponential, the gamma, the inverse gamma, and the Pareto distributions that we look at. So what we end up with is that at infinity for large n, the error, this L1 error is defined over there, behaves in this way. So the first one is a constant that depends on the arrival time distribution and sigma is this index of the regularly varying density of my measure. This sigma appears more or less everywhere. And then n. So with n, it behaves as 1 over n to the 1 over sigma minus 1. I show later in the next slides how this error behaves for different choices of an arrival distribution and also for different sigma. So sigma here is something between 0 and 1, and we see that the behavior when it's close to 0 is very different when it's close to 1. And the closest to 1 it goes, the more difficult things become. Whereas the closest to 0, it's kind of easier and better to approximate. Here, so I have again the error just to kind of remind us of how it behaves in large n. The first graph is showing how does this constant change for different choices of the arrival. And this constant is essentially, so in terms of sigma, is the lowest for the deterministic arrival, which is exactly the inverse Levy construction. And it becomes worse as you use a gamma distribution. And then the worst choice is when you use an exponential. So it's a gamma with parameter 1. However, for large sigma, they are very similar in how they behave, and the differences are more apparent for small sigma, and still kind of close. These two plots, B and C, they show how the error changes again for different arrival times with n. So as expected, for larger n, the error, behaves, it gradually decays. And again, the best error is for deterministic choice. And this is expected because the deterministic arrival time corresponds to the inverse Levy, which is exactly the best approximation in terms of the size. They are almost surely decreasing my weights, whereas the others are not almost surely, they're stochastically decreasing. All right. So posterior inference. How does this behave once we use it inside an actual, like, completely random measure mixture model? So what we talk about, like in the paper, and I'll show here, is two directions. One idea is how can you use the sequential construction? And this is used when you want to do exact posterior inference for the original model. Or alternatively, what happens if you use the IID approximation? Therefore, you're now trying to estimate the approximate model. So the first case where you want to do exact posterior inference for the original model, what we describe is so we describe a slice sampler to obtain samples that are symptotically distributed from the true posterior using the series approximation. And when it comes to, slice sampling for these completely random measure mixture models, there's been a lot. There is choices when the mixing distribution is a Dirichlet or when it's a stick breaking process. And we're specifically here talking about an extension of the slice sampler proposed by Griffin and Walker. When there's these two slice samplers, slice 1 and slice 2, and what we show is that our approach generalizes the slice distribution. I'm not showing this in practice, but the main idea, if you remember this sort of slice sampler they have, is that by carefully choosing the arrival distribution, we generalize the slice distribution and we obtain a Gibbs sampler which has simpler and more tractable updates than the one that they propose, because their sampler is the exact case of our special case with a deterministic arrival. But of course, we also show in the paper that, the practicality and the usefulness, it lies in the regime of small sigma values. As you increase sigma, the practicality is a bit compromised. And, the slice sampler becomes impractical. The number of latent variables you have to sample is huge. So it needs caution on how you use it and what choices you make. The application I show here in the next slide is based on the second part I have. So what happens if you want to do inference on the approximation, on the finite dimensional approximation? And we explain how you can, build a Gibbs or Metropolis Hastings to obtain samples asymptotically distributed from that joint posterior. So the experiment we have here, the simulation study, is the setup is of a standard mixture model where we have our completely random measure here by choice being a generalized gamma process. We have Gaussian mixed PDFs, Curly K. So we assume observations from this model. The random measure for the weights and location is a generalized gamma with sigma being between 0 and 1. It's important because then we draw from this model for different values of sigma, for small sigma, for something around 0.5, and for large sigma. We draw several datasets from these models for these three values of sigma. And what we do is that we estimate the posterior distribution in two ways. Once, using the exact model. So we build this Gibbs targeting the exact model of Avarente. And then we also build the Gibbs sampler that approximates our finite IID model. We collect the posterior samples, and since this is a mixture model, what we do is that we measure the number of non-empty clusters, and we call this K. So we get the posterior samples, we get the number of non-empty clusters. So now we have a distribution for this number of non-empty clusters for the exact posterior and for our approximate posterior, and we measure the Kolmogorov-Smirnov statistics. So the smaller it is, like this, the closer to 0 this statistic is, the best our approximation is, because it means that there's no difference between the exact and the approximate. So ideally we want, everything to be close to 0. The conclusions that we get from this model are the following. Firstly, this on the left is how this difference between the approximate and the exact is for different sigma. And we see that for larger sigma is kind of higher differences, whereas for smaller sigma is not so high differences. And in all cases, orange and green do better. So the gamma rivals, which is orange and green, are doing better than the blue one, which is the exponential. So in practice, choosing those gamma rivals, which give us the exponentially tilde generalized BFRY, which is conjugate to all those other ones. In practice, it did work quite well. And with n, again, we see that for larger n, firstly, the approximation gets better and better. And this behavior of the gamma rival being better than the exponential, again, it holds. And overall, when it comes to kind of qualitatively assessing the results, when we get the gamma rival and we compare the exact and the approximate, they were very, very close. Yes, and I think, this brings me more or less to the end. So we propose this way to have a unified way to give both a series representation and an IID approximation for any completely random measure. We mostly focus on the generalized gamma and the stable beta, which have their own special cases. And then we propose novel series for these two examples, and also show connections between other forms in literature that we see and use so far. We analyze the error both in a kind of marginal way and inside the likelihood. And although I haven't showed it here today, we talk about how we can generalize Gibbs slice sampling for these mixture models, or do this sort of variational inference that I showed. And of course, this can be used in many other kind of actual applications, because here it was only simulations. And one thing that I can only say here is it's used in a couple of applications of this graphs work when it comes to time-varying graphs or spatial graphs. Here, so one is Francesca, there one is Skian, Nike, and Palla, Carolente. They use these approximations to sample graphs from a completely random measure, and it's one of the few papers I've seen kind of that it works very nicely and very well, and I'm also using it at the moment. So yeah, I think this brings me to the end. Very happy to take any questions or clarifications.
Thank you, Xenia, for a nice talk. And we're going to have the Q&A session. So if you have any questions, please raise your hand.
Hi, I don't know how to raise my hand, but I have a question. Is that
okay.
Hi, Raffaele.
May I?
Yeah.
Okay.
Yeah, go ahead.
Thank you. Thank you, Xenia. Thank you. I really like your work. I'm just curious about something that is related with your last slide after the summary. That is yes. How to use this approximation in the graph theory, right?
Yeah.
I never investigated, but it seems to me that you can reach sparsity in the graph when you have an infinite active, completely random measure. But when you truncate, you don't have this infinite active anymore. So you don't have sparsity anymore in the graph. Or you still are able to have a sparse graph with the truncation. I don't know if it's good.
Yeah, you mean if you take the finite approximation?
Yes, if you take the finite approximation.
Yeah, you are actually. So as you said, exactly, when you use a generalized gamma, so for each member of the network here, we have a weight from that generalized gamma, and then the link probability depends on those weights. We get a sparse graph. Essentially, we can tune it to be dense to sparse. But then when we took the finite approximation, which is this exponentially tilted BFRY, it still gives rise to this range of dense to graph sparse, and this paper, you can see that it's being used. I think the other one I have in mind is not published yet, but yeah, it does keep the sparsity. It doesn't break the sparsity.
Oh, okay.
If you choose something else, I don't know, like a gamma distribution or something like that, it does break it. But these choices, they don't. And there are a couple of papers before that that use the BFRY, and I'm happy to send them over.
Okay.
It works. Try.
So it depends on the choice on the latent on the time. So it depends on the choice on the distribution of the time.
On the W's.
Oh, the W. Okay.
The size measure, right? Not the location, but the size measure.
Okay. Okay. Thank you. Thank you very much.
Okay. Any other questions from anyone else? Okay. So then let's thank Xenia again. And the next one will be on the March 6th, which is Wednesday of the first Wednesday of March. Okay, thank you, Xenia.
No, thank you. Have a nice day or evening, or depending where you are.
Bye. Bye. Thank
Bye.
you. Ciao.
Bye,
Ciao.
Xenia. Bye. Thank you.
Bye all.
Ciao, Alessandro.
Thank you. Ciao.
Ciao.